So from in the last topic we stopped at this 5C. Okay, so I'll explain this. They have asked only for 4 marks, so that's a safe thing for us. So they have said us to explain modus ponens and theory of resolution with example. Okay, so now let us see here. Like I said, modus ponens. This is a formula actually. It's in the max, M4 max. P. This symbol stands for and. In the bracket, P implies Q. This is in the bracket. So if you have this kind of thing, then your actual answer will be Q. To explain this, you have to just say that. So say, suppose P, it is if it rains, the ground will be red. So this thing, if P, then Q. If it rains, the ground will be wet, and it is raining. Therefore, the ground is wet. You understood, right, how you got Q here? Simple thing. We are proving a logic over here for an AI machine. So what you're saying? First, you are saying P implies Q. What is P? It is raining. What is Q? The ground is wet. So, if it is raining, P implies Q is what will happen. If it is raining, then the ground will be wet. And you are also saying that and P, it is raining. So, what will that mean? Obviously, it will mean that the ground will be wet, right? So, that's what is the answer here Q. So, that's what they have explained here. See, you just have to say if P then Q. So, what you have to do, just write like this. If P implies Q is in the bracket, if P then Q, then only P. So only P is true, therefore Q. So this how you have to write. Now you just write uh, like this, okay. Even in maths it is like that. So you write like addition type thing. First write this in the bracket, just say what is that. Just write P, then in the bracket write P is true, then just write like this and leave off, okay. That's it. That's your modus ponens like that, okay. And then we also have the sub question, this theory of resolution, right? Even I'll tell what is theory of resolution, okay? Okay, where is cursor? Okay, I will draw, let me draw. So here, actually when I try to copy paste the content, the symbols will not come. So what they're saying, we have one clause, okay? Clause nothing but assume a preposition, P or what is that, Q, okay? And then we also have negation P or R. Okay, so what they're saying, this is one thing. Oh man, just okay, that is one thing. And here, this is another clause. Okay, so now what they're saying, from this two clause, what we can derive is we'll only get the resultant as Q or R. Okay, so what they're saying, so P or negation P will always gives us true itself. So the this thing, to apply the resolution rule, we look the complementary letters, in this case P, and negate negation P, and combine the remaining letters from both the clauses. So what they're saying, from clause 1 Q and from clause 2 R. So resolution clauses 2. So if we apply the rules or resolution rule, so what will happen if you have P and then you have negation P in this complementary letters are there, no? So what we'll look for complementary. If it is there, then what we'll do? We will combine the remaining letters. What they say, if there is complementary letters. Complementary is what? Usually you have studied. This is A, and if there is one bar on that, that is complementary, right? In this max relative, if you have this negation symbol, that is complementary. So if you have P and then negation P, so what will say, the rule resolution rule says that this will go. Let us read this definition. Resolution is a rule of inference used for propositional logic and first order logic. It is particularly useful in automated theorem proving and logical programming. The resolution rules allows us to infer a new clause by resolving two clauses that contain complementary letters. Two clauses which is having complementary letters. If here P is there, in another clause P negation P is there. If here P is there, in the first clause negation P is there. If that is there, we'll group the remaining two letters, and that will be our solution. Okay, that's what it is there for theory of resolution. Now let us go for this A star. A star search to find the solution from. Okay, let me just first search this A star and show you. Okay, oh my god, 963 matches. A star search. Meaning the okay, it's not this. I don't think that's the starting. Greedy base for search. Okay. So see here in A star search, I have this thing. Okay, f of n is equals to g of n plus h of n. Understood? So this is my heuristic function which I am using here. H of n is the cost of the each node. Okay, I'll just show you in the diagram. Here the orange one which are there that are h of n, and the g of n is nothing but the black numbers. Okay, and now don't tell I'm racist here. Just it's in black, something like that. Okay, so g of n and h of n you got to know, right? So f of n is equals to this cost plus heuristic function value. Okay, so that's what we'll be applying here. Just write that we know that the heuristic function used under A star search is f of h itself. F of n is equals to g of n plus h of n. Okay, so what will happen? First, they'll give this here to find the solution path from A to Z. So I'm starting from here, then I'll end at here. Okay, heuristics are with nodes and cost is with edges. Write all the steps as well as open and close list for full marks. So okay, so first what I'll say, open list I'll add A, close list empty. Okay, then what I'll do, I'll see the adjacent nodes from A. So then write for from A you have A to B. Okay, A to B, how you will write A to B, what you have by applying heuristic function f of n is equals to, okay, so you just write f of b here. Okay, f of b is equals to g of n value 4 plus what is this, h of b value, that is 12, which gives us 16. Okay, then it's same way if I do f of c, it's so hard to write from this mouse now. Okay, is equals to, what is g of n, that is 3. What is this one, h of c, that is 11, so it gives me 14. So I have f of b as 16, f of this as 14, so I'll select this one. So now what will happen, A will go to the closed list. After I explore B and C, if I'll put, what I'll do after this step, what I'll write, I'll put A in the closed list, and in the open list I'll have B, C. After writing this, I'll calculate the heuristic function with respect to B and with respect to C. Then with this minimum, I'll select that. So what I will do, I'll add here C. Okay. Now nothing is here in this. What is that, closed list? So now from C, what is there? E and D, right? So I'll write. Come on. I'll write E here and D here. Okay, my open list E and D is there, my closed list A and C is there. Same way I will calculate again, 10 plus 4, 14, 7 plus 6, that is 13. Okay, so I'll select 13 here. Okay, then again which I selected, D will go. So now I have A, C, D. Now in the open list, which will be which will I have? C and D. Since it is undirected, I'll have C and D itself. But I'll select 2 comma 4 because since C is already visited, I'll only go with this E, which is 2 plus 4, that is 6. Then E will come here. From E I have B and I have Z, solution Z. So I'll write in the open list B comma Z, and in the closed list one by one I'll be writing that what is that, these things. Okay, previously also I had done the same thing. If you can see here, here are the previous one. Yeah. Did I get that? Oh man. Answer the following question. Plugins, recent. It's not there actually, it's all gone. Anyways, no problem. Just leave it off. So that's how you will be mentioning one by one and adding the open list, open list, closed list, and you will write off. Okay, so that's it. It is there. I was quiet for a moment because I was texting in my mobile. Don't think so much anything. So for that's it done. One by one, you will be writing like this. In open is there. Like you will be adding one by one all the nodes. So this all will be there in the closed list, and at the end you will get Z also closed list. Open list it will be empty. Then you will get the this one. Then you write path A to C. then A to, then C, from C to D, then like that, E, then Z. Okay, I'll highlight this like this, like this, like this, like this. Okay, you will go like this. And also write the f of n. For everything you have to calculate. Okay, this thing which I did here, you have to calculate this for all the nodes wherever you go and write. That's it, nothing else is there. Now what they have asked, explain contrapositive double implication elimination De Morgan's rule with example. Prove logically that there is no pit in 1 comma 2. Okay, so contraposition. Hmm, is there any blank space over here? So that, okay, wait, let me first show you here. Backward, okay, I did not explain those things. Fine, no problem. Textbook, cancel. If I just touch this, I should go. Okay, it's not happening. If I touch it, I'll go to the index. Yeah, nice. Somewhere, I'm genius. Okay, I'll explain you now. So first you have to, what you have to do, draw. So basically, this comes under Max first module M4. Why did I draw Q? Okay, if you have P, two prepositions P and Q, and P implies Q. Okay, so now what is the contraposition of this? Contrapositive is nothing but, okay, negation Q implies negation P. Okay, so this is nothing but the contrapositive thing of our actual given proposition. So if they ask what is the contraposition, explain contraposition. So you have to give an example. How you will give the example? If, okay, you can take that rain example you just said. Suppose P is something, okay. Suppose P, okay, what shall we take? Something good. Okay, I am rich. Okay, same thing. I am happy. Okay, so if I am rich, I am happy. Okay, this is the given proposition. This is P and this is Q. If I am rich, this thing how it implies, if I am rich, I am happy, like that. Okay, it's implying like that. If, okay, so then what will the contrapositive of this negation? If I am not happy, then I am not rich. That's true actually. So you can write like that. So just write this kind of example. You don't have to show only this much things. Okay. Oh my God, these messages. I hate this text, man. Oh, anyways, just ignore that. I'm explaining here. So see here. You understood right? What is contraposition? It's very simple, man. It says in your max, your syllabus max. You have this in what to say, fourth module, first module of your max from fourth semester. Bloody peoples, they are doing it on purpose. Okay, so if P implies Q, the contraposition of P will be negation Q implies negation P. So don't like directly this. If suppose there are true statements or true prepositions, that is P and Q, in which P is I am rich, Q is I am happy. The contraposition for this statement will be negation Q implies negation P, which means if I am not happy, I am not rich. You understood, man? Then double implication elimination. Okay, this is textbook, right? Let me just go to here. So I think that's something syntax. Okay, so which topic is this? Not here. It will come later. Yeah, syntax and semantics in first order logic, I guess. Is this correct? Was simple. Okay, where is it? Syntax. It should come somewhere here itself. Okay. Yeah, no. Wait, just a moment. Sorry, you can just do double tap and skip, 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 skip. Yeah, got it. See here. Highlight, highlight. Implication elimination. Uh, this nonsense guy did not write completely everything. Uh, P implies Q, contraposition. You can see, right? If A, P implies, so here alpha implies beta is there, then contraposition will be, get highlighted. Contraposition will be negation, beta implies negation, this one. By conditional elimination. Okay, if A, B, then, okay, wait, I have to remove this double, what is that double, what is it? Double implication elimination. Okay, first we'll see De Morgan's rule. So De Morgan's is nothing but Okay, where shall I draw? I'll draw here itself. Simple. You have P or Q, and here you have negation. So what will this give? It's our laws of logic. Okay, De Morgan's. That only you have to explain. So it will be negation P, and or will become and. That's it. Negation Q. Similarly, if we have P and Q, the negation of this, so this will become negation P or negation Q. That's it. That's the De Morgan's law. Okay, I think I have explained this De Morgan's properly, right? You just have to use the same, what is that example you can use. If I, okay, what you will say, I am rich or I am happy. So if you take the negation of this thing, whole negation, then I am not rich and I am not happy. Okay, if you say saying, I am rich and I am happy. So negation is I am not happy or I am not rich. Okay, like that you can just write the sentence in theory, right? Practical. Put these symbols and write. Coming to this double implication elimination, you can simply do this thing is single implies. Okay, we don't want that. So what I'll do, I will erase this. Then I'll just highlight this one. You can see here, right? Biconditional elimination. Biconditional elimination is nothing but just a two-side wala like this. So basically, what it says is, if you have some proposition like P implies Q, and then you also have Q implies P, then you can simply write it as P biconditional Q like this. So that is nothing but your double implication elimination. If not, you can also write like this, like P implies Q and Q. Okay, Q implies R. This will give us P implies R. Okay, that's it. So nothing else is there for us to explain over here. Okay, I think I've done. Prove logically that there is no pit in 1 comma 2. Okay, this is not a see simple thing. Let me go to that Wumpus world place, or else is there any Wumpus world thing here? Okay, 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 okay. I'm not getting any free space. I'll just zoom in here completely. Huh? That's enough for me. So basically, it's like you have this what to say Wumpus world. So what they're saying is they're asking us to prove logically that there is no pit in 1 2 1 comma 2. Array, wait, go. So this is 1, this is 2. Okay, here pit is not. So usually pit is here. Okay, Wumpus is here. Uh, there is pit here too, and here also I think so. And gold is here. If there is okay, you just draw this diagram. Okay, 1 2 3 4. 1 2 3 4. Okay, so they are saying that here pit is not there, Anta. So what you will do? Let us suppose, let us assume that the diagram given Wumpus world diagram like this. So what will say? 1 comma 1 is the starting location from the given diagram. Okay, then what you write? If b of 1 comma 2 is true, true, which means there is breeze in 1 comma 2, cell 1 comma 2, then it implies negation of p of 1 comma 2. So what you will do? B implies negation P. Okay. Hey, why did I do this? Okay, yeah, 1 comma 2. 1 comma 2. Here also you just write in the bracket 1 comma 2 like that. Understood, right? So what you're doing, p of 1 comma 2 implies negation of p of 1 comma 2. So which means if there is breeze in 1 comma 2, then there is no pit in 1 comma 2. Okay, I understood. Like this simple thing you can simply write and leave, because anyway it has asked only for, okay, it has asked for 8 marks, right? So suppose if this is 2, 2, 2, which becomes 6, so remaining 2 marks. So this much is more than enough to explain for 2 marks. Then differentiate backward and forward chaining with example, which was actually written here. Okay, backward chaining versus forward chaining. Backward chaining and forward chaining are two inference methods using logic and artificial intelligence to derive conclusion from a set of rules and facts. Backward chaining. What is the process in backward chaining? It starts with the goal query and works backward to find the facts that supports the goal. Usage often used in goal-driven systems such as expression. Example: goal is prove Q. Rules: P or Q and R or P. Fact R. Step to prove Q. We need to prove P. Okay, to prove P, we need to prove R. Since P or Q. Okay, if you just P or Q, then we have R or P. Okay, so if I have to prove Q, then I have to prove P. If P is true, then only my Q. If Q should be true, okay, then this should be true, or is it like this? P implies Q. This thing, that's the problem actually. To prove Q, we need to prove P. Right arrow or right arrow. It's like this. P implies Q, R implies P. Then to prove Q, okay. So to prove Q, we need to prove P since P implies Q. To prove P, we need to prove R since R implies P. The R is a fact, so P is true. If R is a fact, okay, since P is true, then Q is true. Wow, these things are so confusing, right? Let us take what to say example from textbook. F O oh shit F O R W A R D minus 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 biological. Okay, I have to go up. Oh wow, so many. Okay, actually I have a forward chaining. Yeah, now forward chaining. Okay, here up one now. Oh, I have so many. Down, 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 down. Yeah, yeah. I think it came out. It already came. Forward chaining and backward chaining. Oh, this is normal forward chaining and backward chaining. Okay. Effective. So I should not go here. Or else if I want, I can just check once here. Array forward and backward. No, not from here. Yeah, this is a place. So see a forward definite clauses. So this is the diagram for forward chaining. So for what we do, we remove clauses like this. Criminal is west, and if American is west and criminal is west, one by one. Okay, this thing is for and. Okay, so one. Okay, so this thing, these all things are in and. First, what we'll do, we'll derive that criminal west, okay, or American West and weapon M1 and sells West M1 to Nano and hostile is Nano, which means, see, hostile of Nano means Nano is a hostile country. Nano is draw. Okay, Nano. No, no, sorry, it's not Nano. It's Nono is hostile. Then sells West M1 comma Nano, which means West sells M1 to Nano. What is M1? That is weapon. Okay. Then also we have weapon M1, missile M1 owns Nano M1, which means it has sells West M1 comma Nano. Okay, wait. I'll do one thing best. I'll explain this properly in next video. Okay. We'll see something else. Explain various ambiguities. Okay, this thing I'll just show you the. Hey, let's see if something is there. Fact is R. Rule R P R implies P. P implies Q. Goal prove Q. R is a fact. Apply R plus B. Since P is true, R is true. Okay, then P arrow Q. Since okay, same ulta is letting proving no pit in 1 comma 2. Okay, just see here. What was the question? Explain various ambiguities in natural language processing with example and summarize in the form. Ambiguities in natural language properties. Lexical ambiguity. The word bank can mean a financial institution or the side of a river. Bank, river bank. Okay. Explanation. Words with multiple meaning can cause confusion in understanding the context. Suppose I'm saying, what is bank? So what you will say? Full of money, or you will think like that. No, because we are only greedy. We don't want money. But bank also can be mean as what is that? What is that, man? River bank. Then syntactical ambiguity. Example: I saw the man with the telescope. Explain. The sentence structure can lead to multiple interpretation. Who has the telescope? So here we are not defining this man properly. So who is having telescope? So for all man, it can be anyone from the man. There exists X from all from for all X like that. Semantic ambiguity. Example: the chicken is ready to eat. Explanation: the meaning of sentence can be unclear. Is chicken eating or being eaten? The the chicken is ready to eat. Okay, so here, okay, the chicken is ready to eat. So now the hen or the chicken, it is ready to go and eat. Or else the chicken is ready, so now we will eat. So what is this? This is semantic ambiguity. Then we have pragmatic ambiguity. Can you pass the salt? The literal meaning is a question about ability, but the intended meaning is a request. Can you pass the salt? So here, what is happening? Misunderstandings. The way, okay, some two people, one will always misunderstand like that it is. The literal meaning is question. Okay, so here what will happen? They are questioning the ability. So are you capable of passing the soil? So this is not the computer will think like this. No, natural language, it's a human will understand, but computer will understand. So these are the four things I have explained. If you read once, you will understand. Then the what is that? Ontological commitments and epistemological commitments. Propositional logic, first order logic, distribution logic, modal logic. We have to talk, which completes and different. Okay, that's done right. Then define universal and executional instantiation and give an example for both. Prove the following using backward and forward as per law. And okay, as per law, this thing. Okay, very this thing I'll explain the second video. Okay, guys, thanks. Hit the subscribe button and enjoy or do rock in the examination. Bye.
Can I please ask you to subscribe? That's all we want, man. Just press subscribe.